In this lecture, I will give you a small introduction to the Smith chart. The Smith chart was invented 1939 by a guy named Philip Smith, and he was sick of doing all these complicated calculations involved with transmission lines. In order to simplify this, he came up with a tool, a graphical tool, which does all the calculations for him without the need of using slide rule or something like that. So in the following, I will give you some background information on what is the Smith chart all about and how it's designed. And after that, I will give some basic applications of the Smith chart. Well, what's the basic idea? The basic idea of the Smith chart is to calculate automatically the relation between the load impedance of a loaded transmission line to the reflection coefficient of a loaded transmission line. And this relation can be calculated by this well-known formula I am putting in a box here now. And it's basic. It's easy to calculate because you only have to plug in the information into that formula and you get a result. However, there's one big problem. ZL is usually complex, and that makes also gamma to be complex. Calculating complex numbers is nowadays easy using computers. However, in the 1940s it wasn't, because doing this calculation it's quite tedious when you deal with complex numbers. In order to simplify these things, Mr. Smith had this idea. Can we solve this equation using a graphical tool? And he developed the Smith chart. The first step is to normalize your load impedance ZL. ZL can have a big range of values. In order to make it easy to use in a graphical chart, we have to normalize it. That's why we normalize our load impedance by the line impedance. And the line impedance Z0 is often, very often, 50 ohms. No? So if I don't say anything, what I mean is Z0 is 50 ohms. No? So once the load impedance is normalized, we call it Z prime, as you see here. Z prime means that you have a normalized impedance. Please note that the impedance usually is measured in ohms. However, the normalized impedance is just a value without a unit. When you plug in that ratio in the gamma formula, you see this now. And well, you divide everything by Z0, and now you can replace this fraction by Z prime L, and you get a new formula. Gamma is equal to Z prime L minus 1 over Z prime L plus 1. Now we want to find a graphical tool for solving this equation here. Well, so what's the problem actually? The problem is that ZL prime as well as gamma are complex valued numbers. A complex valued number you cannot express in a simple function sketched as a curve on a sheet of paper. So because we deal with four-dimensional space here, no? ZL has 2 dimensions and gamma has 2 dimensions. So what we have to do is we have to map all possible impedance values, which are in this complex plane here, to all possible gamma values, which are in this plane. And when you think about it, you will see that the impedance is usually has a positive real part. There are no negative impedances in the real part, unless you have something really fancy. And the imaginary part can have any value you can think of. That makes the possible area of impedance values in the complex plane this orange-brown area here. On the other hand, the gamma value is restricted to gamma values with magnitudes less than 1. And the magnitude less than 1 means it's inside a circle which has at the maximum value 1. No? There are no reflection coefficients larger than 1 because that would mean that the reflected wave is bigger than the incident wave, as long as you have a passive load. That cannot happen. So what happens now? One impedance value here can be mapped to a gamma value, and actually any impedance value you choose here can be mapped to a unique gamma value in that plane. So our goal is now to find the graphical mapping between all the impedance values you can have to all the gamma values you have. And there's always a unique relation between the two. As I said, this is called a mapping. A mapping is a general mathematical term, but in our case it means we map one complex number z to another complex number gamma. And since this function is a conformal mapping, that means that any gamma values, maybe go back here, all z values that form a circle. So when I have here lots of z values that lie on a circle, they will also lie on a circle in the gamma plane. The circle can have a different center and a different radius, however, it's still a circle. We have to note that even a straight line like this one here, let's use a different color so I'll make it clear. Let's say we have a line that looks like this. A line is a special circle. It's a circle with an infinite radius. No? So even a straight line can be mapped to a circle here, or a circle here could be mapped to a straight line here. No? So that's what conformal mapping means. This information is useful when we construct the Smith chart. That's why I mentioned it. Now, let's go through the whole process now. On the left side, I have my complex plane of the z primes. Here I have the complex plane of my gammas, and I marked already in yellow the area that is allowed, and here the hatched area that is allowed. Now we can play with that, and I can let's start with red. For example, I can mark that point 1 here. The point 1 for z prime, when I plug in 1 minus 1 over 1 plus 1, this becomes 0. So this point here maps to this point here. When z prime is 1, it's due to the normalization, that means it has the same value as z naught. So that L is equals to z naught. That makes it the match point. From the physics side, when gamma is 0, there's no reflection. That means when ZL is the same as z naught, then z prime is 1, and that makes gamma 0. No reflection. Another extreme case would be when my ZL is 0. That means no impedance. Impedance is 0. That means it's a short. So 0 minus 1 over 0 plus 1 becomes minus 1. So my 0 value here, the short, maps to a gamma point at minus 1. Minus 1 is the reflection coefficient of a short. And the other extreme would be infinite, which I cannot show here on my slide. It's somewhere up here. Infinite minus 1 over infinite plus 1 becomes 1. So the infinite value becomes this value. Maybe I draw that here as this little thingy. So that now we have already mapped 3 points from the left z prime plane to the right gamma plane. Now let's use some more points. For example, the point 2. 2 minus 1 over 2 plus 1 becomes 1/3. So this point 2 is somewhere here, 1/3 is somewhere here. The point 3 is 3 minus 1 over 3 plus 1 is 1/2, which would be somewhere here, I would say. And so on and so on. Maybe 4. Well, I don't do 4, then I have too many points. So this is kind of boring because these are only real numbers. Let's go for some complex valued numbers. For example, j. J minus 1 over j plus 1. Well, that's something that's not easy to calculate. Either we do it on a sheet of paper, or I use my prepared thing. Sorry, I have to open up a new tab here. So, in order to do the calculations, I open the Jupyter Notebook or Jupyter Console, which is a Python program. And with this tool, it's easier for me to do some calculations. That's why I'm going to use it. For example, I want to calculate the gamma value for z of 1j. A z of 1j becomes a gamma value of z minus 1 over z plus 1. That's the one missing. It's 1j. So 1j as gamma value stays 1j. That's interesting. So this j becomes here this value. Or minus j, doing the same calculation, becomes actually here minus j. So what happens when I say when I use 1 plus j at this point here now? 1 plus j becomes what? Well, let's go back to our Python console. Let's make it here in the center. Now let's go. Let's make z as 1 plus 1j. Do the calculation again. I get 0.2 and 0.4j. So this point becomes 0.2, which is somewhere here. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, it's somewhere here. So 0.2 and 0.4 is here. So this point actually goes here. Oops. So 1 minus j, let's do that one. 1 minus j becomes, when I do the calculation again, 1 minus j, 0.2 minus 0.4. So it's the same but mirrored on the other side. So it's here. 1 plus 2j, how about that? That would be here. 1.2j plus 2j becomes 0.5, 0.5. 0.5 is here and 0.5 is here. No? So it's somewhere here. And the same for the negative. So, and how about we also use 1/2 plus minus. So it's 1 plus 0.5j. It's 0.05 and 0.23. 0.05 is very close here and 0.23 is somewhere here. It's the same on the other side. So for the fun of it, I can also maybe do 1 plus 5j and minus 5j, which is not on my graph here, but I want lots of points. 0.86 and 0.34. 0.86 is somewhere here and 0.34 is somewhere here. So this point up here and then down here, somewhere here. So now I get something interesting. So I have this point here and also I have this point here. So take a look. When I connect all these points, I'm walking along the real where my real part stays 1 all the time. When my real part stays 1, this line, remember it's a conformal mapping, is mapped to something like this, and this must be a circle. So we get for, oops, that should be a circle. No? This line is mapped to this circle. No? This line marks points where my real part is 1. No? So Can do the same again for, let's say, this line here. Let's pick some point for this line. And I forgot to mention one thing. This point goes to infinity, no? And J infinity is the same as infinity, as we can see from the Riemann sphere, which I don't want to get into. So actually this point infinity must be also involved in that circle, which is here. No? So the same for 2. 2 plus J, what is 2 plus J? Let's calculate this. 2 plus J, the reflection coefficient of 2 plus J. Sorry, 1, I need a 1. Is 0.4, 0.2. 0.4 somewhere here, 0.2 is somewhere here. So there's something like this. And the same for the negative, no? And this point we have already, which is this one here, no? Let's do this again. Um, 2 plus 2j is 0.53, 0.53, and 0.3 is somewhere here. Negative. So you see when you do this line, and I have marked these 6 points here, then I get a circle which looks like this. Oops, and it's not a very good circle. So I can repeat the whole thing for 1/2. And 1/2. Let's make the real 1/2 here. Oops, no. Yeah, like this. Then it's minus 0.33. We are here. So we know that it becomes a circle which looks like this. Slowly I'm getting there. So, good. So these are 3 lines that are mapped to these 3 circles. Now we can repeat the same thing for, because before I do that, I maybe mark my points here. That's for 1, that's for real part 1/2. And this one here was for real part 2, no? So, oh, and also, maybe before we go to the next step, we can mark the line with pure reactance, no real part, no? Like a capacitor or an inductor would be like this. Then, oops, that's really bad. Then we are on this point, this point becomes a circle, so actually it becomes this circle here, no? So this outer ring describes reflection coefficient, so the magnitude of 1, which relates to impedances with the real part of 0. No real part, no power consumed. That means everything is reflected. So, okay, now let's repeat the same thing for horizontal lines. Horizontal lines means we have constant imaginary part, for example, this line here, no? And we have tons of points here already. We have this point, this point, this point, this point, and the infinity point. Actually, that is this point, this point, this point, and this point. And when I connect these points, since it's not a complete line, it's only a section of a line, this line gets to this section of a circle. So this is my line for my imaginary part is equals to 1. Can do the same thing for the 1/2 point here, here, and here. Maybe let's find that point again. Which would be 1/2 j, no? 1/2 j is minus 0.6, 0.8. Minus 0.6 is somewhere here, 0.8 is somewhere here. And maybe we can also find one more point just for the fun of it, which is this one, 0.5 plus 0.5. J. So that's minus 0.2 and 0.4, which is somewhere here. So this point and this point we have already, which are these 2 points here. So and that makes that blue line here, well, not extremely good, but that's when my imaginary part is 1/2. The same I can do for the negative j's, and you see already that it's the same thing, but it's all mirrored. So these two lines actually become this line here and this line here. So this is imaginary part is minus 1/2, and this is imaginary part is 1/2. So I forgot the minus sign here, sorry. So and can also do 2, for example, here. We have lots of points here too. 2j, maybe you can calculate 2j is 0.6 plus 0.8j. 0.6 is somewhere here, 0.8 is somewhere here. So we get these 2 points. Also include this line. That makes this band go through this point here, no? Something like this. So that would be imaginary part is 2. So now I hope you can see that. Oh, actually, and again I forgot, the real axis is also constant. Imaginary part, when the imaginary part is 0, we move on that real axis, no? So that would be imaginary part is 0. So and now you see the idea. Lines of constant real part, the red ones, become these red circles. Lines of constant imaginary part become these blue bands. And now the magic starts, because now we can do the following. I can mark a point, for example, my z prime supposed to be as 2 plus 1j. Well, where's my point 2 plus 1j? 2 plus 1j is this point here. Yeah. So this point here we can find on the gamma plane by knowing, well, my real part is 2. Since my real part is 2, it's on the circle here. And my imaginary part is 1, so it's on this band. So this makes this point to be found here. Once we found that point in the gamma plane, using our spider grid, we can find the imaginary part, the imaginary value, and the real value of my gamma. Or, if I like to, I can also draw a little arrow here, and I can find the length of that arrow is my magnitude of gamma, and this angle here is my angle of gamma. And that's the main idea of the Smith chart. Forget about the left side. We only need the right side, because now we can pinpoint using the spider net here any impedance in the grid, mark it, and then read off from the underlying Cartesian coordinate system our gamma value. And that makes it possible to convert z prime to gamma. And we can also do the backward if we want to. So when you draw it professionally, it looks more like this. You see all these circles. The circles are usually marked with the values of the circle. So that's, for example, here's a circle for marking a real part of 0.6. The bands are the imaginary parts. Here you see it's 2j, 4j. This, for example, is a band that marks an imaginary part of 4j of the impedance, and so on. We also see our special points here in that chart. The center is the match point, where it's 1 and imaginary part is 0. The short is where everything is 0, and the open is where everything is infinite. Everything on the lower half in the Smith chart is negative j values. Negative j values means capacitive. everything that's in the upper half of the Smith chart means it's inductive. So coming back to our example, when I have a real part of 2 and an imaginary part of 1, then I can use my real part circle as this, my imaginary part bend is this, where they intersect, that's where my point lies. And now measuring this length and angle, I can find the gamma value. A real professional chart looks something like this. We're going to work with the professional chart later on. It has some more information on it, which we're going to use later on. The Smith chart, when you look at it, is also a fantastic way to visualize where is infinity, because you see when you go towards this point actually marks my infinity point, which is kind of a philosophical question. Where's infinity? In the Smith chart, it's easy. It's at a single point. There are artists like Escher, for example, who did very similar things, and a lot of people actually say that the Smith chart is just a special way of interpreting Escher's painting. Now you see also here, when you come towards the edge of the circle, you go towards infinity. In Escher's painting, infinity is not one point, it's just a ring. No? Okay. So let's come to the applications. The very first application is to convert a Z value, a Z load value, to a gamma value. No? We have done that in the examples already. I'm going to do that in a systematic manner again, so you see how it works. Let's take our chart again, and I'm dealing with, an impedance Z of 10 plus 30 ohms, 30 J ohms. So when I normalize that, I get a Z prime, which is my Z over Z naught. Z naught I assume to be 50. Then this becomes 0.2 plus 0.6 J. So this is my normalized Z value now. So I mark that point in the Smith chart again. Maybe I go and take a different color here. Real part is 0.2, which is a circle. Imaginary part is 0.6. This band here where they intersect. I get my point of interest. Let's get rid of these lines here. So this is my impedance point in the Smith chart. It's also marked here. Now we can draw the gamma phasor, so the arrow, and the length of that arrow is my magnitude of gamma, and the angle towards the real axis, which is usually not shown in the Smith chart, is this green angle here, which is my angle of gamma. So we can measure here, the total length is 1 to the rim, so the fraction of it is actually 0.74 when you measure it. We do this in the real examples later on again. And the angle I can measure with a protractor, and I get 116 degrees. So and that makes my gamma value here 0.74 and 116 degrees. More examples and how to go backward and how to use the real Smith chart I show in a separate video, which is a hands-on video called Finding Z from Gamma in the Smith chart. So if you want to stop now and take a look at these examples. If you want to continue and look at the examples later on. Because we have more things to introduce. Actually, there are 3 more things. The 2 I show you today. The third one is a separate video. Line transformation to the Smith chart. And that's something that makes life easy compared to using the calculation with a calculator or with a PC. What we can do actually is we can find from a load impedance ZL. Let's go to another color again. From a load impedance ZL, we can find the input impedance here, Zin, of a loaded line using the Smith chart. And we can do this extremely efficiently. Well, what's the theory behind it? Let's talk a little bit about the theory, not too much, so you just get the idea. The gamma 2 value here at the load is my incident wave U2 plus, and the reflected wave U2 minus, the ratio between the two. On the input side, you get another gamma value, which is a ratio between U minus 1 to U plus 1. So when you put all information together, and you get more thing, there is a phase delay between U2 plus and U2 and U1 plus by the length of the line, the electrical length of the line. No? So the phase difference between the two is beta L. No? So my U minus 1 is the same as U minus 2, but with an additional delay of minus J beta L. No? That's well known from transmission line theory. The same is true in the other direction for the ratio between the two plus voltages. They are delayed by e to the J beta L, but this time it's plus because 1 is in time before 2. No? So now I can plug that into to find gamma 1. Gamma 1 is U1 minus over U1 plus by definition. Replacing this by the U2s gives me that. And then I see this here is actually nothing else but gamma 2. And e to the minus J beta L over e to the J beta L becomes e to the minus 2 J beta L. So when you put this all together, I write it down here again in big. Then gamma 1 is the same as gamma 2 plus a phase delay of minus, let's make it maybe a different color here, 2 J beta L. So we have a phase difference, or let's call it angle difference. Sorry. Angle difference of 2 J beta L, which is 2 times the electrical length of the thing. No? So 2 times electrical length. So on, this information is useful when we go to the Smith chart. Because let's assume here we know gamma 2 and we want to know gamma 1. Well, let's assume gamma 2 is in the Smith chart somewhere. So just for the sake of an example. Now, in order to find gamma 1, we know the magnitude doesn't change, only the angle of the two gammas change. And the angle, the change in the angle, in German Winkel, is 2 beta L. So all we have to do is we have to rotate this point about the center, rip by 2 beta L, and we get the new gamma value. Once we get the new gamma value, we can read off the spider grid our input impedance. So when you go back, I know ZL. I convert in the Smith chart to gamma 2, then I rotate, I get gamma 1, and then I read off the Smith chart Zn. That's all. So once again, mark ZL in the Smith chart, read off gamma 2, add the angle, means rotating about the thing, read off gamma 1, convert in the Smith chart to Z, and I have my input impedance. Calculating the input impedance with a formula is a lengthy task. Remember, there's these tangents over tangents formulas. Well, again, one little example. We start at the point 0.2. Let's go back to orange here. So yeah. We start at the point 0.2, 0.4J. 0.2, real part, 0.4J, imaginary part is this point here. No? So once we found the point, we mark it here. No? Oops. So it's also marked here. No? So this is my starting point. Now I have to add the length that's related to 0.3 lambda. the length that's related to 0.3 lambda. Let's do the calculation here. 0.3 lambda means I have a phase shift of 0.3 of 1 lambda. 1 lambda is 360 degrees. So it's 0.3 of 360 degrees. No? It's 180 degrees. So this thing introduces a phase shift of 180 degrees. So when I feed in a wave here, it comes out on the other side with 180 degree delay. So since the rotation is always 2 times the phase delay, and the reason for that is because the wave goes in the one direction, gets reflected, and comes back, I have to add 216 degrees in total. So this point here is rotated by 216 degrees when I take a protector, and I can read off my new value here. So, and then I can read off my new value is 0.4 minus 0.19J. That's my new impedance. That's actually my input impedance. And it's my normalized input impedance. I have to multiply it by 50 in order to get the real impedance. So that's how you insert a line without using any calculations in the calculator with the tangents formula, just using the Smith chart. Okay, since we do this fairly often to insert lines, there's a special ruler here on the edge of the Smith chart. The ruler is called wavelengths towards generator usually. No? Or let's call it lambdas just. Or give it a different color so we see what's going on. Lambda towards generator, it's called. Towards generator because somewhere here we have a generator, and when we move our impedance from the load side to the generator, we rotate actually always my point in this direction here. No? So, and this ruler here helps us to determine the amount of rotation, because you see it starts at 0 lambda, and then here it's 0.25 lambda, and then it becomes eventually 0.5 lambda. So it tells me how much more lambda is inserted that rotates the point. No? Coming back to our example, we start at let's go here. We start at 0.062 lambda. We insert 0.3 lambdas in length. So we have to add here 0.3 lambdas in order to get to our endpoint, which should be 0.362 lambda. Now I have to follow that ruler here, and then we see 0.636, 0.362 is here. So, and that's the amount of rotation. We just take a ruler, draw that line here, same distance as from here. It's very helpful to have a compass, and then you can do that. Okay, that gives me the endpoint without using a protector. No, you don't need a protector because we always have that ruler on the outside rim. Okay, that's the example. As I said, there are more examples and separate videos to show you how it works. So there's a video called Inserting a Line, which explains that. Okay, now the last trick we learned today about the Smith chart is how do we transform from Z to Y? Well, on a sheet of paper it's easy. An impedance Z is the same as 1 over my admittance Y. When you deal with complex numbers, that can be tricky. And sorry, I wanted to see that. I want to go to this slide first. So, so you see that you have this very simple relation. However, when you deal with complex numbers, that's not that easy because you have to do the conjugate complex and extend it, and then you cross out whatever. So it's a lengthy calculations. You can simplify this process a lot using the Smith chart. And just the theory behind it, how it works. Well, when you have a gamma value, it's z prime minus 1 over z prime plus 1. So when we replace the z's by gammas, we get 1 over y prime minus 1 divided by 1 over y prime plus 1. We can multiply it here, everything with y, and then reorganize. Then we get y minus 1 over y plus 1 minus, there's a minus sign here in front of it. No? So. And this is important because we can put it now on the other side, and we see that my gamma value can be also calculated using the y's. However, this is just the negative gamma value of the y calculation, from the z calculation. So when you look at it, and actually I forgot the primes here again. When you look at it, calculating gamma from z gives you the same result as calculating it from the y's, but with a negative sign. And we can make use of this in the Smith chart. And that's a slide I was reordered. So when I calculate the z, I get a value here in my as gamma, which is the blue thing. And the negative of this is just the mirrored example, gives me this point. And this point is my y value. Sounds confusing, and it is confusing. However, when I give you an example, I think it becomes clear. Basically, what it means is, sorry, I have to go. Z prime and y prime are in the Smith chart always related by just the mirrored point on the other side. That's what it basically means. I have an example, but I show the example a little bit later. Now, there was some guy who had the idea, well, we can, rather than using the Smith chart here shown in red, we can also use a so-called admittance chart, which is basically like a Smith chart, but everything is flipped. No? You see here's 1j, this becomes the 1j down here, here it's minus 0.5j, that becomes 0.5j here, and so on. So everything is flipped, and then you get a chart which looks like this. No? Again, this relates all my y values to my gamma values, because here behind we still have our gamma grid, which does the same thing. So the only difference is in the blue chart now I plug in the y values, but I don't plug in the z values. So when you know the y value, it's better to use the admittance chart rather than the impedance chart or the Smith chart, because then you can directly mark the point here and they can read off your gamma value. When you have an impedance, it's better to use the Smith chart. When you convert between impedance and admittance, you have to mirror the point. In order to put everything together, someone, and the name is unknown, had the idea to put the two charts in one chart, and then it looks like this. Extremely confusing, but also extremely technical. So if you want to impress people, show them this chart. No? So now, by finding a number in the z-plane, I have, for example, here, well, the point 1 plus 1j is this point here. In the Smith chart, and this becomes in the admittance chart this point here. No? It's on this circle and it's on this band. No? The circle is 0.5, so my y value now is, real part is the circle is 0.5, and the imaginary part it's minus 0.5. So without doing any calculation, I can find from the z value my y value and vice versa. Just putting on the red goggles gives you the impedance part. Putting on the blue goggles gives you the admittance value. Well, let's double check that in our program just for curiosity. 1 plus 1j 1 over, no? Becomes 0.5 minus 0.5j, no? Do this on a sheet of paper, it's actually a lot of work to do that. No? Okay. So at the end of the day, we put two charts on top of each other. Below we have our reflection coefficient, gamma chart, which is not really shown, but you measure it. Then you put on top your blue admittance chart, and on top of that you put your red impedance chart. And you stack all three on top of each other, and there's always a unique relation between an impedance Z to an admittance Y and to the reflection coefficient gamma. These 3 points always are uniquely combined, and by using the 3 combined charts you can read off all 3 values at once. This is how the chart looks like when you put everything together. As I said, it looks confusing, and the lines are very dense here. In reality, when you see a sheet of paper, it's not that dense, and you always need a ruler to measure the gamma values, which you usually read off down here. No? Let's see. So I have a lot of examples coming up how to use this chart. No? This is just to get you the idea. Okay. Yes. So yeah, I have the example. I have the example for conversion and impedance Z to admittance Y in this extra video, and it's easiest to show it in a real chart, because then you have the blue line and the red lines, and you can measure it using the rulers. So there's a very lengthy example of, I think it's 10 minutes, 15 minutes long, that show you how to convert Z to Y and vice versa. You can also use that to combine two admittances. Basically, when there are two impedances in parallel, you combine the admittances. It's also explained in that video. Sorry, maybe you take a look at this video now. If not, you can look at it later if you get the basic idea. Let's do a last complex example. You can see the power of the Smith chart. I have a complex circuit here. I have a load impedance of 100 minus J25. I put in series a capacitor with minus J25. I have a line here with 0.3 lambda, and I assume this is 50 ohms here, which I didn't put in there. And I put in parallel an inductor with J50 ohms. So the first thing you do before you go into the Smith chart is you normalize everything. So this ZL becomes, well, everything divided by 50. Huh? So this becomes 2 minus 0.5J. That's my normalized ZL. This becomes minus 0.5J. This becomes just 1. And this becomes 1J. No? Now we have all the normalized values because everything divided by 50. Okay. Now, how you find Z4, the input impedance? How do you find that? Well, we go step by step, coming from the right. No? First, we mark our point Z1 or ZL in the Smith chart, which is, as I normalized it on the page before, remember, here, 2 minus 0.5J. 2 real part is here, minus 0.5J is here's minus 0.6, minus 0.4, so it's somewhere, it's in the center between, so it's a line somewhere here, no? Oops, a little bit to the left, sorry. So 0.5 is a line that goes like this, no? So, and it intersects here, so that's my point to mark. So that's my Z1. I found that point here, no? So now I add in series minus 0.5J. No? So that makes 2 minus 0.5J. Minus 0.5J makes it minus 1J. Minus 1J is this red line here. No? So that gives me a new point, which is here, no? When I put the capacitor in series. Shown here on the next slide. This point, when I have Z2, moves to this point. So now I'm here. I'm standing here and looking into the circuit. Now I add my 0.3 lambda long line. Well, how do I do that? I mark my start point, which is 0.288 0.7 lambda. I add my 0.3 lambda to it. That gives me my endpoint, which is 0.587 lambda. So now we have the problem that actually 0.5 lambda is off my grid here, of my ruler, because after one complete revolution it starts at 0 again, because this is 0.5 lambda here, no? And this actually would be 0.6 lambda. So in order to, whenever you go over the 0 line here, all you have to do is you have to subtract minus 0.5 lambda in order to get the modulo of 0.5, no? So which makes it 0.087 lambda, which is this point here. Then I draw that line and take a compass, and I end up at this point here, which is my Z3, which is 0.5 plus 0.5j by incident. So we're standing here now, no? Oops. So, and looking into my circuit. No? So next step is put J50 in parallel. Now, since it's in parallel, we have to add the impedance Z3 here with this impedance J50 ohm here. No? The impedance Z3 we can also express as a Y3, and we can do that by reading it off the blue grid. Now, maybe I go in blue now. On the blue grid, we're on that blue circle here, and we are on that blue band here. No? So the blue band is minus 1j and the blue circle is 1. So actually this is in blue 1 minus 1j. So one thing you always have to keep in mind is the upper half of the blue grid is now negative and the lower part of the blue grid is now positive. And often the negative values are not marked in the Smith chart because people assume as an engineer you know that. No? So negative reds values are down here, negative blue values are up here because everything is mirrored. No? So this point here, my nice point, is 1 minus 1j. So we have to put now the y value of my inductor in parallel. The y value is was j, the z value, make it in red. The z value of my inductor is 1j normalized. No? That makes the y value to be minus 1j because it's 1 over j. No? So we have to add now minus j to my y3 in order to get the total y's. No? So we had 1 minus 1j. Now we have to add minus 1j. So we add up at 1 minus 2j. So we add this point now. So once again, y3 prime was 1 minus 1j. The y value of my inductor is minus 1j. That makes y4, the total admittance, 1 minus 2j. And this point is this point over there. No? So maybe in green here. So we are ending up at this point. Once we are at this point, we know our y value. We can convert this now back to my z value. My z value, z4 prime, is reading off the value on the red grid. Right? The red grid is real part is 0.2. Imaginary part is 0.4j. So my normalized Z4 value is 0.2 plus 0.4j. denormalizing it, make this everything times 50, 10 ohms, make it here, plus 20 ohms, 20 j ohms. So this is my final input impedance, no? And let's see if this works here. Yeah. So only using the Smith chart without using any calculators and a sheet of paper, we can find the input impedance of that complex structure. There are more examples coming up in the online lectures and in the videos, so please stay tuned. However, this is what I would like to do for today. Just to summarize, when you have a point here, and let's go back to the pencil. When you have a point here, well, when you put a capacitor in series, you decrease the imaginary part and the real part stays the same. So the real part is this circle, it stays the same, and the imaginary part becomes smaller. That's why you move down here. When you put an inductor in series, you move up because the real part stays the same, but the imaginary part increases. When you put a resistor in series, the imaginary part stays the same, but the real part becomes bigger and you move along that line. You cannot move in this direction because that would mean a negative R. When you do the same in parallel, you move on the admittance chart, the blue chart. No? An L in parallel stays, the real part stays the same, so you go up here with the negative value because now it's negative in the top, and putting a C in parallel moves it down that circle, and putting an R in parallel moves you along that band. You can also see the extremes. When your R becomes, the admittance of your R becomes extremely big, basically you have a very small resistance, then you go towards the short. No? When coming back here, when you put in a resistant and the resistance becomes bigger in series, you go towards an open, which is this point down here. Okay, more examples about this coming up, so I think you get the idea after a while. When you put all manipulation techniques into one slide, you see this. You can get out of a point with 7 different ways. CLR in series, CLR in shunt, or putting a line in, then you move along that black line which circles around the center. Okay, the next would be the impedance matching with the Smith chart, where you do the opposite. So I try to match arbitrary impedances to 50 ohms. This is something I do in a separate lecture because it is there are a lot of tricks involved and I want to show you in a different lecture. Okay, this concludes this lecture and I hope you stay tuned and I see you again soon.